let's go ahead and get started. It's week 4, almost Halloween. Which so I posted this in the email. I sent this out in the email and I posted it, but um Friday's lesson is going to be moved to Saturday morning. I do apologize, but because it's Halloween, a couple people reached out, asked about it, and then I myself, I could make it happen, but it would be a little tricky for me as well. So since it's just a Q&A, I figured probably wouldn't be too big of a deal. We'll still record it, but we're going to do it Saturday morning at 8 a.m. Um, Appreciate that. Yeah, so Friday's Q&A and giveaway session will be Saturday morning, 8 a.m. Pacific, so that's 11 a.m. Eastern time. But yeah, so just wanted everyone to know that as many people as possible. I'll send it out in another email and post about it again, I'm sure, just make sure everyone gets it. Okay, so before we get to the questions, we're going to cover wake turbulence and ground effect, left turning tendency, adverse yaw, density altitude, and then we're going to go over scheduling the FAA written exam. And we're going to look at our schedule, and I am going to try and encourage everyone to get it on the schedule. And then I believe we'll have to look this up when we do that, but I believe it's 72 hours. You can change the schedule up to 72 hours without having to pay again. So we'll pick a date for everybody. We'll schedule it wherever you are. We'll kind of do that together. And then if for whatever reason this course, takes a little bit longer, if it takes a little bit longer for you, we'll have everyone kind of set an alert for their date 3 days before to or 4 days before, or even sooner, to make a decision on whether they need to reschedule or not. But I think having that schedule will be another kind of kick in the butt thing to make sure that we're on top of our homework and getting everything done. So we'll go over that, how to do that, because I know there's questions about that. And if the FAA PSI testing website is working, because today it was not working, and then I finally got it to work, and then it said it's undergoing maintenance for the next 7 days. I was like, of course. 7 days is a long time to be under maintenance for a website. But anyways, whatever. It's the FAA, I guess. So any questions? Let me pull up the homework. Any questions on the homework? So this needs, gosh, I keep getting these dates messed up. Sorry about that. Let me pull that up to fix. But it's this right here is what we're talking about. This was the homework that we assigned on the 27th. It's due today. Yeah, that's true. They're probably not paying anyone. So they just say it's under maintenance. True. With the government shutdown. Well, it's PSI though. I don't know, but I guess it's their FAA portal, so maybe. That's okay, Sherry. We'll record it for you. And we can answer any questions when you get to that point. But that'll be part of your homework, is to schedule that yourself. Um, how do we figure out minimum safe altitude anywhere regarding glide speed? Good question. So what is the minimum safe altitude requirement for the FAA when you're anywhere? What's like the overarching FAR for minimum safe altitude?
Isn't it any altitude where you can land safely without due hazard to property or persons?
Yes, exactly. Then once you get into those other areas like lightly populated or you know, I can't remember, sparsely populated, and I can't remember the other name, congested, right? Then you start getting specific altitudes and clearances. So your question is, okay, but that's the FAA requirement, but how do we do that safely? How do we make sure we don't land into anything? Or how do we, more importantly, not maybe not more importantly, but how do we make sure that we land safely? So that is all about the glide distance that your aircraft is going to have. So the pilot operating handbook for your aircraft is going to tell you a glide ratio. So the glide ratio is going to be the amount of distance on the top of the ratio over sorry, I was reading the chat. So the amount of distance you can travel while gliding over the amount of altitude you lose. So we can think of it in feet. It kind of gets, you kind of got to convert because we're used to thinking about miles in terms of distance, but feet in terms of um, altitude. So you kind of have to convert to feet for the distance. But generally, for general aviation, it's 10 to 1 for a good glide ratio for aircraft. But you'll want to know the glide ratio for your aircraft. But let's say it's 10 to 1. So that means if your engine is out and you have no power, you have to glide. That 10 to 1 is at the best glide speed. Remember, we talked about that max lift over drag area, that angle of attack. That's kind of the same thing, but we target a speed if our aircraft doesn't have an angle of attack sensor. If it had an angle of attack sensor, we'd target the that angle of attack that gives us the max lift over drag. But usually it's not going to have it. So we're going to use the best glide speed, which is the same thing, just kind of converted to speed in our pilot operating handbook, POH. So once we do that, that's when we get the glide ratio that 10 to 1. If we're not at that, we're not going to get our best glide ratio. So it goes down. So that's very important. That's why, the first thing to do is to when you lose an engine is, again, we talked about ABCD. That A is airspeed. You want to trim for that glide airspeed to give you the most amount of time in the air and most distance to travel in the air. So you'll want to kind of plan, you want to think of this when you plan your flights and you plan any sort of flight. You want to have this in mind and kind of it's hard and it depends on how meticulous you want to be. But if you are over an area that you cannot land, let's say it's, forest or jagged rocks or, downtown city or something like that, you'll want to make sure that you are flying over that at an altitude where if you lost engine, you could then glide with your glide ratio to somewhere that's flat enough for you to land. A parking lot, an airport. Ideally, it would be some sort of airport, but maybe it's an open field or a parking lot or something like that. Does that answer the question, Kay?
Yeah, I think that's helpful. What I'm worried about though is during like emergency procedures or when you're practicing emergency procedures and you go through your checklist, that I think we just automatically say, glide speed, and then you just assume that the altitude that you have plus your glide speed is going to make for a safe landing. But I
Mhm.
don't know what the altitude distance would be. Like I think that something we should do is practice even in the practice area when we're flying, that we should like know it rather than just saying glide speed and altitude. I don't know
Yeah,
what the altitude would be.
yeah, and I think there's some shorthands around that, but they use and I believe in ForeFlight you can do that. Basically, you can overlay on your, I think they have to tell me if they have this or not, but I think it's ForeFlight. Basically, you can, if you have your updated aircraft in ForeFlight and it knows your glide ratio, wherever it shows you on the chart, it'll put a ring around you, and that's the radius of where you can glide to.
I didn't know what
Yes,
that
it does have
was.
it.
Okay, cool.
Yeah. Yeah. So that's a very valuable tool because then you don't have to like do the math or anything like that. But it's still good to plan when you're planning your flight, right? To think about that and have, you know, when you're looking at your chart, have some sort of distance in mind that equals your glide ratio to be like, okay, here's some things over there. I'm good there. I'm good there. I'm good there.
Great, thank you.
Mhm.
Hi, Nick. I have a question on a stall homework.
Yeah, one second. I'm looking at Darren's comment
Okay.
here, 29th. Yeah, yeah, Darren, that matches what I have. I just am saying that I need to change the date at which it's due. Because it says October 29th, and that's the same day as the assigned date. That's what I was trying to say when I said I think it's wrong. But that looks like the same I have, the thing that you sent, Darren. Okay, sorry. Who was that now that I covered that and looked at that, I'm ready for the next. Was it Hassan?
Yes.
Yeah, what's your question?
So I have one question in a homework, like two questions. I don't know how to do it.
Okay.
It's in a stall.
Okay.
So the first question is saying refer to figure 278. If an aircraft normally has a stall speed of 54 knots, but the bank of 60 degree, what is now the stall speed?
This one right here? Or
Yeah.
was it?
Oh, yes, this one.
Okay. Okay, so let me pull up the figure for us. Give me one moment. I don't know why. I keep forgetting to have that just prepared for the session. All right, so it says if an aircraft normally has a stall speed of 54 knots, but is in a bank of 60 knots, what is now the stall speed? Okay, so let's go to 278. All right. So this is a little bit blurry. I need to fix that. Sorry, guys. Figure 278. Okay. But I think we can see it well enough. All right. So this on the y-axis is percent increase in stall speed. On the x-axis, it's bank angle. So we're told the bank angle is 60 degrees, right? 60 degrees. So we want to look here on 60 degrees and find the corresponding percent increase in stall speed. So if we look at 60 and we go up here, this curve hits 60 right on this line, nice handy line for us. So if we follow that over, that equals 40% increase in stall speed. So our stall speed is before, straight and level stall speed is 54 knots. And I just said 40. So if it increases by 40%, so 40% of 54, we can find that by 54 times 0.4 is 21.6 knots. We add that to 54 knots and we get 75.6 knots. I think you could do the same thing. You could just do 54 times 1.4 and that'll get you the same thing. Yep. I like to do it the other way just because it makes more sense to people. Yeah, so we're finding 40% because we know again, why do you guys know why the stall speed is increasing here? Can you tell me that in the chat? Nick says increased load. Yeah, the load factor. Yeah. Cole, you're not wrong. But yeah, load factor is the what we want. So as we increase bank angle, we increase our G forces, our load factor. And when we're at 60, that's quite a bit of bank, quite a bit of G's. So it can increase our stall speed by 40%, which is crazy. And so we want to find 40% of our stall speed. Our stall speed, it was told to be 54. So we find 40% of that and then add it to the previous stall speed of 54. So we get about what did I say, 70 something? Does that make sense, Hassan?
So I understand the first part, but I didn't understand the second. So I understand like when it's 60, we got the 40%, and I didn't understand what should I do next.
Okay, so we have 40. We know it increased. This is our stall speed, 54 knots. Before that's our straight and level stall speed. So when we're just flying straight and level, we have no load factor, no G forces. Our stall speed is 54 knots. That's going to increase by 40% when we're in a 60-degree bank. So we just need to find the number that is 40% more than 54. So there's a couple ways to do that. The shortest, quickest way is to just do 54 times 1.4, because you're essentially saying 54 is going up 140%. It's going up by 40%. So that's 1.4. Or we can do 54 times 0.4, which is we're finding 40% of 54, which is like 21, and then adding that to 54. Does that make sense? Or maybe I need to draw it out.
Makes sense, but I have a question also. So can we use like a calculator in the test, a written test?
Yeah, so
Because I'm bad in math, so I don't know how to do it, to be honest.
yeah, so if you're bad at math, you're gonna just want to remember the procedure. So you're gonna remember whatever percent increase, just make it a decimal and add that to 1.
Okay.
So like if it's 40%, make it 1.4. Okay, so
Okay.
1 point, and then you add. So if it's 40%, make that 0.4 and then add it to 1, and then multiply that by 54. Those should be the
Okay.
steps that you remember. And that'll get you the answer. But yeah, so there's a little calculator that pops up on your testing computer at the test center. You can also bring a calculator, but it has to be like unprogrammable and not, it has to be like a basic calculator. And then also on the electronic E6Bs, there's also calculators built into those if you know how to use those.
All right. Thank you.
Mm-hmm. All right. Any other questions on the homework? Okay. Oh, Assam, you got one?
I have one, but do you have time or?
Yeah, yeah.
So I have one more question in a stall too.
Okay.
It's saying refer to figure 2. If an airplane weight 3,300 pound, what's the approximate weight with the plane?
Yeah, right here.
Yes. Yeah.
Okay, so refer to figure 2. So let's go to figure 2. Uh, there we go. Oh, geez. I went past it. Figure 2. All right. What's figure 2? All right, so very similar curve where we have bank angle on the x-axis and load factor on the, well, on the other curve we just saw, it was percent increase in stall speed. But this one has load factor. Okay, it also has a table. This is telling us the same data. This is just this on the right is literally just a graphical representation of what is here on the left. Okay. And this is an actual FAA figure. So this is, if you get a question about load factor and stall speed with banking, it's going to be using this figure if you have to use a figure. So it says if an airplane weighs 2,300 pounds, what approximate weight would the airplane structure be required to support during a 60-degree bank turn while maintaining altitude? So this is another way of testing your knowledge on load factor. Load factor is the increased amount of weight that your aircraft has to be able to support, because you've probably heard like when G forces go up, when they do those like tests that you weigh heavier than you are. So that's true. So like I got to go on NASA's Vomit Comet. So NASA's Vomit Comet is like this um specialized Boeing jet where they just do these giant uh parabolas. They do really high climbs and then the really steep descents. And during that descent, you actually get less than one G forces. And so you get what they call microgravity, and it simulates like you're in space. So you can get up to like almost 0 Gs during that descent, and you can do like tests and stuff. And then when I was in college, we did a test on like sorting lunar regolith, which is like lunar soil. Anyway, it was really cool. But we got to do these, and so for like 30 seconds, we'd be like weightless, and we'd have to run our tests. But right, so the reason I'm telling you this is because in that you go weightless, right? Your weight gets less, and you float in the air, right? Well, the opposite, when you increase your G forces, you get heavier. So whatever the G force is or the load factor is, we simply multiply that by our weight to get our new weight. Just like Tim said in the chat, our weight is 2,300. He meant 2,300. And then we just got to find the load factor. We just multiply the load factor by the weight. And that's that new weight, the weight times the load factor, is what our aircraft is feeling during that steep turn. It's feeling those G's and it's feeling that force. So the structure, the bolts, the aircraft struts, all that has to withstand the force of that weight, that new weight in those G forces, right? If it doesn't, then they'll just break off. So like when they're designing planes, they can't just have a plane be able to withstand straight and level flight. They have to think of, okay, when are these at what G force can this plane get up to? With our certain aerodynamics and our ability to turn at these angles and stuff like that. And what is that new weight that we have to support with our structure? So that's kind of what it's getting at. So what we need to do is, it says 60-degree bank and it's 2,300 pounds. So we look at our figure and we look at 60-degree bank, we go up, and that's a load factor of 2. Okay, so right at 60, we go up, we find the curve, come over, it says 2. So we basically need to multiply our weight, 2,300 by 2. So Tim, you said 1.154. That would be a 30-degree bank. So if we had a 30-degree bank, we would look here and they're like, okay, well, that's kind of hard to read. That's why this table's here, 30-degree bank. Oh, the exact one is 1.154. Oh, there's a question that asked for 30. So yeah. So we get that load factor, then we just multiply it by our weight. And that's the weight that our aircraft has to support during that turn. So 2,300 times 2 is what? 4,600. Does that make sense, Hassan?
Yes, thank you so much.
Yeah, of course. All right. Well, let's get to today's lesson, and then we'll stop in between for questions. But I want to get to this because it's got quite a bit of slides to get through. All right. Let's go. Okay, so we want to talk about wake turbulence today. We talked about the vortices that our wings make, especially really heavy aircraft, and they make these vortices because of lift. Remember the induced drag, the pressure differential from above and below our wings at the wing tips and at the back of the wings, they rush together to, find equilibrium, the high pressure versus low pressure, and they create these spinning vortices, and those propagate downwards and create induced drag. They also have quite of other kind of secondary effects. One, if you can imagine this big plane flying through here, if you are a small airplane like what we flying through this, that could be pretty dangerous. That could push us. Look how strong this is. That could push us down into the ground or flip us over if we're in one of these vortexes. They're very, very dangerous for small aircraft to fly into. Usually one of the reasons why you don't see a lot of training facilities and aircraft flying at Class Bravo airspaces, because if they did, they would have to, and they're lined up right behind a Boeing, 737 or whatever, they would have to wait a long time for these vortices to clear to allow that small aircraft to safely take off. Okay, so we're going to talk about wake turbulence. We're also going to talk about this ground effect, which also comes from these vortices. So the more lift an aircraft generates, the stronger the wake turbulence is, I should say is, because there's a bigger differential. So the more lift, there's a bigger pressure differential. And so when they meet at the end of the wings, there's stronger, mixing and stronger vortices. Vortices are highest. Let me get my little pointer here. Vortices are highest in slow, heavy, and clean aircraft. And clean means no flaps, landing gear, not extended, no payloads like weapons, external takes, etc. That's kind of what it means by clean. So you have your landing gear up, you have your flaps up, you have no payloads attached to the wings. It's completely clean. So vortices are the highest in slow, heavy, and clean aircraft because those are the types of situations that produce, again, the most lift. So that's why the vortices are highest there. A slow, heavy, and clean aircraft happens to be the exact configuration of large passenger aircraft during a climb out. So private pilots must be well aware when taking off or landing after one of these aircraft. Again, we're not going to be doing this at Class Bravos a lot behind these Boeing 737s, but you may be in a situation where that happens. But even small private jets that have turbines on them, those can get pretty heavy, and those can create wake turbulences enough to flip our small aircraft. So even the smaller private jets can do that. And so sometimes you'll hear ATC warn you about wake turbulence, or they might have you wait for wake turbulence. But it's also good to know, that it's there in case ATC is trying to rush you to take off. You might be like, hey, I want to wait for the wake turbulence. I don't want to do that, or something like that. And you can ask them if you can wait. So, good to know. Even turbine powered private jet. Okay, that's what I just said. All right. To avoid wake turbulence. So we want to avoid this, right? And we can't just ask ATC to let us wait it out forever. So we kind of just have to fly and avoid it. So when landing, a pilot should touch down before the rotation, which is where the wheels come off the ground, point of a wake turbulence generating aircraft that has just taken off. So if we visualize this, we're this little guy here. We're landing, and a big jet just took off. Private jet, large jet, whatever, just took off. We want to land and stop before their takeoff point, because once they take off and they have enough lift to generate, taking off, that's kind of the point we want to avoid. So we want to land before that. And you kind of think of, again, it propagates behind and down. So any area below its climb path. So if we kind of make a triangle here, any area below this, we want to avoid. So another situation when landing, a pilot should descend above the aircraft's approach path and touch down after the touchdown point of a wake turbulence generating aircraft that has just landed. So in this situation, we are now landing after a large jet or larger aircraft that has just landed. So they just land, and then we are landing after. In this situation, again, their approach path is like this. So anything below that, we want to avoid. So we want to kind of go past where they landed and then touch down after where they touched down to avoid their things. Sam, you have a question?
Yeah, I did. Can you go back to the last slide, please? Yeah, thank you. So if we were coming into land in this particular scenario with a small Cessna or whatever, and we're coming into land, and for some reason we should get down pretty quickly, but we can't. We're getting closer and closer and closer to that. We need to go around. Are we then going to get a big old whack of wake turbulence as we now go around because we're then going into that like that dirty air that's coming from that jet?
Potentially, yeah. But if you were to go around, you'd want to go around and stay above this triangle area below their path.
So if you were going around, you would just want to try and gain as much basically altitude as quickly as possible.
Yep. Yeah,
Yeah,
and
okay.
that's going to be the same as what we talk about here in the takeoff scenario.
Okay. All right. Sorry. Thank
No,
you.
no, you're good. So to finish off the landing, so we have, I kind of came up with a mnemonic because, I mean, once you kind of look, you draw it out. That also helps you to remember. If you just remember, hey, I got to avoid anything under their climb out path or their approach path, then it makes it pretty easy to know where to go. You just have to avoid those areas. But I came up with a mnemonic lattle bar. Land after aircraft touchdown, land before aircraft rotation. If it works for you, it works for you. If it doesn't, I recommend drawing it out on a piece of paper to remember. All right, so now let's talk about taking off. A pilot should rotate, again, that's wheels off the ground, at a point before the point of rotation and climb out above the climb out path of a wake turbulence generating aircraft that has just taken off before them. So that's kind of a mouthful. But if the needed climb performance is not available in your aircraft, which kind of, Sam, you're talking about, pilots should maneuver upwind if there's a crosswind from heavy aircraft takeoff point. And if that is not even possible, if there's not a crosswind and you don't have the climb performance, then you just need to wait. You need to wait for that stuff to settle down, basically. Dissipate. This is the word I was looking for. All right. So what does all those words mean? So we have a jet taking off before us and we're taking off. So we just, again, this is kind of your scenario. Even if we were to come down to land and we think, oh, shoot, we're not going to be able to stop before that, we can do a go around and stay above their path. If, again, we believe we have that climb performance. And then we'll get into what I mean by the crosswinds here in a sec. We have a visual that explains that. All right. And then also when taking off, pilot should rotate wheels off the ground at a point after the touchdown point of a wake turbulence generating aircraft that has just landed. So again, this aircraft has just landed. This is approach path. We want to stay below, or we want to avoid anything below that because that's where the vortices go to. So we would ideally taxi onto the runway here, because even in taxi, these can be kind of dangerous. So if we taxied on into here, that could be kind of dangerous. So ideally, we do want to taxi to a point on the runway after their touchdown point and then take off after that. A possible mnemonic for that is TAT-T bar, take off after aircraft touchdown, take off before aircraft rotation. All right. The vortices of wake turbulence are affected by winds just as an aircraft is affected by winds. So let's show kind of what I was talking about with the crosswinds, and the winds also, maybe a tailwind as well. They also add to the hazards that we have to keep in mind. So let's say this aircraft is taking off and there's no wind. So, or let's say it just came into land and it landed right here, and then now it's rolling out. And so these are the wake vortices. They're kind of like this, and they're propagating down towards the ground. And this is no wind. So they're just going to continue to kind of look like this shape after the aircraft lands. Now, if you have a tailwind, it's actually going to keep these from, it's kind of going to push them up a little bit, kind of have them hang out more instead of propagating behind more. Just going to kind of not have a huge effect, but if you look, the touchdown point. It kind of moves above the touchdown point. The wind is kind of pushing these vortices just like it would anything else, right? Kind of pushes these vortices up the runway. Now, in a quartering tailwind, which this is one of the most dangerous tailwinds to have with wake vortices, because if you look, it's actually pushing those vortices right onto the runway, because it's got a little bit of a crosswind component, so it's pushing it this way to the right, and then it's also a tailwind, so it's keeping them on and up the runway. It's just the worst situation you can imagine for a wind, because it's placing these vortices right on the runway. Now, if you had a crosswind, same thing. It's going to push these. And where that comes into play is if you're taking off from 27 right here, right behind it, and you have, the crosswind could push these onto 27 right, just like we talked about. But also, this shows that even if you have a parallel runway and you think, oh, because you might think, oh, I'm safe, I'm not on the same runway as that large aircraft. But if there's a crosswind, it can actually push those vortices onto your runway if it's right next, like 27 left, 27 right, which a lot of airports have. So even if you're not taking off on the same runway, you can still be affected by these if the crosswind is pushing them onto your runway. All right, any questions on wake vortices before we continue?
You talked about a tailwind, but what about headwinds? What kind of effect does that have?
Yeah, so headwinds are going to just they're kind of the best scenario winds,
Right.
because generally they'll push them kind of off the runway. They don't necessarily push them off the runway, but if there was any direction that we would want to push them, it would be backwards. And that's what a headwind does. Yeah.
Right. Does that reduce the time from when you could land? If there was heavy headwinds, would that reduce the time from when you could go in and land do you know what I mean?
Yeah,
Or would it?
I think technically it would, yeah. Especially compared to like this quartering
Yeah.
tailwind. That
Right.
would make them linger longer and in the place you don't want them to be. Okay, so now let's talk about ground effect. So these same vortices, even our small aircraft, have these vortices, and they're created by lift. Anything that generates lift has these vortices coming off of it. And we talked about induced drag, that net downwash. These propagate downwards and they contribute to our overall drag, which slows our aircraft down. And that net downwash also kind of reduces our lift a little bit. Again, like I said before, kind of imagine like induced drag is like someone, and you didn't know, someone hooked a wire to the back of your airplane, and then now you're dragging something heavy. Okay, it's going to want to pull you down a little bit, but also backwards a little bit in both components. That's what induced drag does. So it has a negative effect against our thrust with drag and a negative effect against our lift with this net downwash. When we're close to the ground, this negative net downwash effect is reduced. So the ground kind of quickly dissipates these vortices, and you get less kind of the net downwash sucking force from it that wants to pull our aircraft. The ground kind of helps us out here, and it reduces the effects of induced drag when we're close to the ground. But once we get away from the ground, we no longer feel the effects of ground. So you'll actually feel this when you're taking off, especially if you do like a short field takeoff. So short field takeoffs, we want to essentially get off the ground as soon as possible. Similar to like a soft field takeoff. We want to get off the ground as soon as possible. So what we can do is we can get off the ground earlier in ground effects, and then we can stay in ground effect until we have enough speed to then fly out of ground effect. Because when you're in ground effect, let's say the amount of lift you need to take off is 1,000, whatever, energy units, newtons or whatever. Let's say you need 1,000 units of lift to take off and climb out. In ground effect, that's reduced to like, let's say 900. Okay, you only need 900. So you could take off earlier when you have less lift and less airspeed. But if you were to just continue to take off, you wouldn't have enough lift. So you got to be very, very careful that the lift you need to rise above the air in ground effect is not the same as what you need to climb out. So when you do like a short field takeoff, you'll get in the air, but you'll stay like 5 feet above the air to then accelerate, get to the speed you need to have enough lift, and then take off. But what that does is it gets you off the ground faster. So if you have a short field with no runway or a soft field where you don't want to get stuck in the mud, you can get off the ground faster, then kind of accelerate in this imaginary runway 5 feet above the ground, and then take off out of ground effect. So this kind of visualize that. They usually say that it starts, the ground effect starts at the distance equal to your aircraft's wingspan. So if your aircraft's wingspan is about 20 feet, which is about what our trainer aircraft are, that once we're 20 feet above the ground, we start to feel the effects of ground effect. Okay. And then once you're about 10 feet, it reduces the induced drag by about 10 to 20%. Once you're within 5 feet, 30%. And then 2 feet, about 50 to 60%. So, if you are landing, there's also a consideration of ground effect. And this is why, if those of you have started lessons and you're trying to land and it's like kind of hard and you keep floating, it's because of ground effect. Okay. So you don't need as much lift to stay afloat. So once you get real close and you want to flare, when you're flaring, you're adding angle of attack, which increases lift. Now you're in ground effect, which increases lift. So now you just have too much lift and you don't want, your aircraft just doesn't want to fall down. That is why you have to be so good on your airspeed and so precise on your approach speed, because of any excess airspeed, you're going to just continue to glide in ground effect because of that excess lift that you get. So even a 10% reduction in induced drag can allow an aircraft to be airborne at an airspeed 2 to 3 knots less than normal. And then we mentioned that at 2 feet or 5 feet, it does it by 30%. So 30% is what? 6 to 9 knots. So you can imagine that's a lot. So if your takeoff airspeed is 60 knots, that means you can get off the ground at about 53 knots in ground effect if you stay close within 5 feet. But again, you wouldn't want to climb out of that, because once you lose that ground effect, and if you're too slow, you'll stall. So pilots should be aware of ground effect both during takeoff and landing. During landing, the decrease in induced drag means that any excess speed, which I mentioned before, on your landing, approach, and flare will cause considerable floating. And if you continue like that, you continue to float, it will lead to either a very rough landing, poor landing, and embarrassing, or one that even damages the aircraft or causes an accident. So I think usually they say couple seconds of floating and then just go around, right? If you flare and it's a couple seconds and your airspeed is not going down or anything like that, and you keep floating, or you gain altitude or whatever, you just want to go around. You don't want to mess with it. In takeoff, ground effect is most likely to result in becoming airborne before reaching recommended takeoff speed. And we can, again, I mentioned in short field takeoff or soft field takeoff, we can use that to our advantage as long as we stay in ground effect until we reach that takeoff speed. But this can be pretty dangerous if we're not aware of it. All right, so this is an FAA figure that just kind of shows. So ground effect decreases induced drag. So here's where taking off. Airplane may fly at a lower indicated airspeed, so maybe we can take off at a lower indicated airspeed because of that ground effect. But if we stay in ground effect, we can accelerate. If we stay at this level where we have ground effect and we accelerate to one of our takeoff speeds, then we can, pitch up and continue off until we leave the ground effect area. Now, I have a video here that hopefully will work. Oops. This is the crash I was telling you guys about the other day. So what do you guys think this person did wrong Can you guys all see that?
Yeah.
Okay. So any
Can you
guesses
play it?
on?
Can you play it again?
Yeah.
Thank you.
So there's a couple things they did wrong. Let's see if you guys, I think I mentioned them last time, but yeah, it's awful. I know. Sorry, but trying to use it as a teaching moment. Yeah, so let's say their takeoff airspeed is for that airplane like, I don't know, 80 knots or something. And so he apparently this pilot wanted to fly over these people filming to get a good shot. So he's thinking as he's coming, I think it was he, I don't know. As he's like right here, I have to get airborne so I can turn and make it for these people. Bad idea so many times. So he's lifting off. Let's say his takeoff speed is 80 knots. He's lifting off at like 70, 75. Okay. Which he can lift off, and that's what you see him do. He can lift off in ground effect, but once he gets too high above ground effect, that speed is no longer going to work and he's going to stall. But also, he doubles down on making it worse by entering a hard bank, and that increases his load factor. That also increases his stall speed, and he just can't fly anymore. So enough of watching that. I know we don't like watching that, and I usually try and keep things positive and not show those things. But I thought it was I just popped up on my feed, and I thought it was a good teaching moment, especially for what we're talking about. Pilot debrief. Yep. Um. Yeah. Yeah. I usually don't like commenting on those things because, um. Anyways, I guess I broke my own rule there, but it's pretty obvious what went wrong on that one.
I think it's a good teaching thing though. Like I mean,
Yeah.
it sucks, it really does, but it is good to see and know and learn from it, you know.
Yeah, I hate the people that like kind of almost like profit off
Criticize.
those
Oh,
crashes, and
yeah.
you'll see like there'll be a big crash, and people will be like, let's analyze what happened, and they'll make a post
Yeah.
on it on
Yeah.
Instagram, and I before they even know like what the issue was. So I usually don't like to like post on that and
Yeah.
stuff,
I
but
think all the good, really good, reputable ones usually don't make any comment. They might explain what happened, but they really keep away from kind
right.
of, all
Yeah.
that stuff. Yeah.
Yeah. All right, so any questions on that before we continue to the next subject? Okay. So let's talk about left turning tendency. During training, you're going to hear your instructor tell you to use right rudder. So who here has had their CFI say right rudder to them if you've started flight training? Yeah, Sam has. Ivan has. Yep, yep. Yeah, so there's lots of jokes in aviation world about that because students never really fully grasp uh, kind of always having to use some right rudder. Well, the reason why we always kind of have to use right rudder is left turning tendency. For a single engine, and this is not for every aircraft, right? If you have multiple engines, this effect gets reduced. There's different effects. If you have, jet engines, it's different. But for single engines where that propeller is in the front, there's also aircraft where propellers are in the back, like a pusher, they call them. But for single engine propeller aircraft, like the ones we fly in training, Cessnas, Cherokees, there are several factors that contribute to our aircraft wanting to yaw to the yaw and roll to the left without any pilot input. To counteract this left turning tendency, we have to use right rudder. So that's why they're always saying use right rudder. There are four forces or factors that contribute to the left turning tendency. There's torque, there's gyroscopic. Can you guys see my purple guy? Yeah, okay, then I don't need to use my
Yes.
my red thing. Torque, gyroscopic precession, asymmetric thrust, and spiraling slipstream. So we're going to talk about each of these. Manish says, as long as ball is centered, we are okay, right? That means we have, yes, that's your indicator for coordination on yaw. So yeah, you want to keep that ball centered.
Nick, the more advanced aircraft, like, I don't know, an A380, like, do they have a similar problem? I'm assuming they have systems that are built into these more advanced aircraft that constantly keep it shifting more to the right than to the left, and it's just because we're in like much smaller, older aircraft. Is that kind of a thing?
I think when you have multiple engines, one on each side, it's much less of a factor. They do have things like that, but they also, as someone who worked at Boeing doing trade studies on improving efficiency, they look at everything. And if you're always kind of having to correct yaw here and there, even if it's an autopilot doing it, that's going to reduce efficiencies. And just even the smallest 1% of efficiency saves these companies, these airlines, millions of dollars in fuel. So I would say the more advanced aircraft you get like those, the less and less that happens. But I'm sure there's still some factors that I don't know of. There, like the weight of fuel. If you have more weight in one wing of fuel than the other, that you have an imbalance in your CG, which can cause, movements and things like that. So, yeah.
Thank
Yep. All right. Asymmetric thrust is also sometimes called P factor. You might hear it called P factor. I don't know where that comes from. I think that's an old like physics term or something. But these are noticed the most during high power, low airspeed, high angle of attack operations. So can you guys tell me, when are we high power, low airspeed, high angle of attack? What part of flight are we, or parts of flight? Takeoff, on takeoff. Yep, takeoff and climbs too, right? We could be at a specific, we could be at 2,000 feet. We want to climb to 3,000 feet. We go high power, we pitch up, go lower airspeed. That would also, yeah, climb. Good. All right. So the first one is torque. So torque is a turning force about an axis. For pilots, torque from the propeller shaft is of importance because of the resulting force applied to the aircraft. So the propeller spins right here. So we got this spinning propeller, which is connected to the engine, right, by the propeller shaft. So there's a propeller shaft here that is connected to the engine, and the engine is, those pistons and crankshafts are making that propeller spin, but the engine is connected to that, making it spin, and our aircraft is connected to the engine. So the spinning of that propeller shaft is going, according to Newton, is going to have an equal and opposite reaction. So our spinning propeller shaft this way, our aircraft is going to naturally want to spin back the other way, just a little bit, because our aircraft is heavy. So the weight and the force it takes to spin our aircraft is less than it takes to spin the propeller, because it's much heavier, but it still over time has a little bit of a reaction. And when we're floating in air, has a little bit of reaction. So that would cause a banking kind of roll action that we have here. And there's I found some cool GIFs of each of these. So we have the spinning propeller, and then the opposite kind of reaction of our aircraft is going to cause that motion. Tim, wouldn't the manual of the aircraft recommend a default level of trim to offset the tendency? A lot of aircraft don't have yaw trim or roll trim. Most of them just have pitch trim. But yeah, that's kind of what Sam was alluding to too with autopilots. That's essentially like a new age trim, that these more advanced aircraft would have some sort of trim system to offset that for sure. All right, the next one is gyroscopic precession. So when a force is applied to a gyroscope, the force is manifested 90 degrees ahead of where it was applied in the direction of rotation. So this is the same error that we talked about with our gyroscopic instruments. Remember, we talked about gyroscopic precession with like our heading indicator. That's because our gyro spinning, and if there's any force applied to that from, let's say, we bank or climb or something like that, it kind of adds a momentum for some inertial forces to that gyroscope. It applies a force 90 degrees ahead of the rotation, and over time that kind of adds up as a little bit of an error called gyroscopic precession. So I think the visual will really help on this one, but basically if we pitch up or down, so if we pitch down, we're essentially adding an inertial force to the top of our spinning propeller, which is kind of acting like a gyro. So our resultant force is 90 degrees ahead of rotation. So our aircraft, most American aircraft, the propellers spin this way, which is clockwise if we're looking at it from the cockpit. So a resultant force would be like right here. And so if we add a resultant force here when we're pitching down, it's going to make our aircraft yaw this way to the left. So that gyroscopic precession has an effect on our aircraft. So here's a good, I think, visual, or maybe it's not, but basically you get a force here and it's going to be applied. I think I don't know. I don't know if that's better or not. But so if we're talking like a clock, so when you pitch down, you're essentially putting a force at the 12 o'clock of the spinning gyro, our propeller. And so at the 3 o'clock position, again, if we're looking at it from the cockpit, that's where the resultant force is going to be applied, which is on the right side of our aircraft. Again, looking at it from the cockpit, which will push yaw us to the left, yaw our nose to the left. David said also changes with power setting. All these, the torque for sure. Was that about torque? Yeah, the more power, the more torque force. That's why when we're full power and we have a high angle of attack and we're slow, the full power part of that goes with torque. Do southern hemisphere propellers mostly go counterclockwise as you are looking at it from the flight deck, or I don't know about that.
You said American propellers, most American propellers go that way. I was curious if it kind of worked that for the majority in the southern, they went the other way.
It's just the way they design them in America. American companies just have them. I think it's the American standard kind of. I don't know. It's not an actual standard or rule. It's just most of them spin clockwise. I'm not sure why, but it's just how they design them. Yeah. All right. Asymmetric thrust or P factor is next. So asymmetric thrust or P factor is due to the shape of the airfoils on the propellers and the different angles of attack each propeller blade feels when the aircraft is pitched up. So again, we talked about high angle of attack. This is the one that has a high angle of attack contribution. So when we're in a high angle of attack, like taking off, climbing, this is when we get this asymmetric thrust or P factor. So just like a wing, the propeller blades are designed to cut through the air and create a lifting force, except for it's just in a different direction, in the direction of forward movement or thrust. But you can think of our propellers as basic little wings that we spin around and create lift, just constant lift as they spin around, creating propulsion forward or thrust forward. It's basically all they are. So remember when we talked about lift and we talked about, well, when we have more angle of attack, we get more lift. So same thing with our propellers. Now here, when we're on just a straight and level flight, the angle of attack with our propellers is the same. So one propeller is going up while the other one is going down, right? So on one side, the propeller is going up on a 2-propeller system. At the same time, it's going down. They're spinning around like this, okay? So when one goes up and one goes down and you're at straight and level flight, the loads and the forces, the amount of thrust they create are the same. Each blade creates the same amount of thrust when you're at straight and level flight. When you're pitched up, the one that's coming down, the aircraft propeller that's coming down, has a higher angle of attack than the one that is going up. So the propeller that's going down creates more thrust than the propeller that's going up. So when we have an aircraft, an American-made aircraft that has the propeller spin this way, clockwise from our view in the cockpit, that means the propeller is always going to be coming down on this side. And that means we're going to get more force on the right side from this P factor, right? So we're going to get more force over here and left force over here when we're pitched up. And that force on this right side is going to cause us to yaw to the left. And this kind of is going to show us first the angle of attack of the descending blade. I'll keep it on this because there's a lot of information here, but basically here's the force, more force on the, I kind of went too fast. Let me see if oops, I don't think I can pause it. We'll just watch it a few times, but more force on the right side, pushing the nose, yawing the nose to the left. And it's because the propeller that's going downward when you're pitched up has a greater angle of attack with the relative wind than the other side. So you get more force. P factor is propeller factor. Is that what it means? Oh, okay. I thought it was something fancier. All right, next one is spiraling slipstream. We talked about the spiraling slipstream when we talked about interference drag. We talked about how this prop wash can kind of come up and disrupt the airflow going over our wings. Well, crazily enough, I don't know if that's a word, it can also kind of wrap itself around the aircraft. And in most trainer aircraft, the way they're designed, it'll wrap itself, and mostly the majority of it pushes on the left side of our vertical stabilizer or our rudder. And when it pushes our tail this way, when it pushes our tail to the right, our nose is going to go to the left. We're going to yaw to the left. So I like to, visualize a boat propeller in water and the trailing spiral of bubbles. Well, it's the same thing happening with our propeller in air. We just can't see the bubbles. Can't see that, prop wash. But that prop wash again, it depends on how the aircraft is designed, but on trainer aircraft, it can push, it kind of ends up pushing us on the left side, pushing our tail to the right and pushing our nose to the left. So this is a good show of it here. So it kind of wraps around, pushes on that left side more than it does on the right side, causing an imbalance, causing us to yaw to the left. I'm not sure, Tim, if it's this from the right side or left side. I think you're getting prop wash hitting both sides, but because of, I'm not sure, I think it's the clockwise rotation of it and maybe the size of the aircraft. It hits more so on the left, causing an imbalance of forces and causing the tail to be pushed to the right. Yeah, this is one of the better gifts for sure. All right, any question on left turning tendencies? Okay, yeah, it is different with high wing, but I believe it's still there. So I'm asking this quick Google AI search. Yes, spiraling slipstream is a left turning tendency that affects both high wing and low wing aircraft, though its effect is most pronounced during low speed, high power situations like takeoff. So again, that's probably because the wings are less in the way when you're at a higher angle of attack. And so the prop wash can kind of have more direct access. It'd be interesting to see like wind tunnel smoke of this. I bet that's somewhere out there, a video of that, which would be kind of cool. All right, let's talk about adverse yaw. There is an opposite yaw effect whenever you roll or bank an aircraft a certain direction, and this is called adverse yaw. So it's adverse to where we're turning, where we're banking. So that's why we call it adverse yaw. So we yaw in the opposite direction of where we want to turn. This happens at every single turn. This is another reason why you got to use rudder in a turn to coordinate that ball on your turn coordinator and make sure it's center. So where does yaw, adverse yaw come from? All right, so here we have our handy diagram that we've used like 5 times, right? We're rolling to the right. That means our left wing is up. So we have our left aileron down, creating more lift, and our right aileron up, creating less lift. That causes our left wing to rise. And then we get that horizontal component of lift, which pushes our aircraft to the right, and we turn to the right. Now, remember, so induced drag. So induced drag has had an effect on, right, those vortices behind our aircraft, and that so the vortices behind our aircraft have contributed to wake turbulence, they've contributed to ground effect, they've contributed to drag with induced drag, and now they're also going to contribute to adverse yaw. So those vortices are creating induced drag, and so where the wing that is getting more lift is also getting more drag. So the wing that goes up in a turn is getting more lift, so it's getting more drag over here. When we have more drag over here and we have less drag over here, that makes us want to yaw in the opposite direction of the turn, right? Think of this drag as like someone pushing this wing, right? And that would cause the nose to yaw to the left. And it's because we have more induced drag on the side of the wing that we have more lift. And the opposite would be true, right? Here, if we're rolling to the left, we have our right aileron down, creating more lift, making our horizontal lift vector and helping us turn to the left. But because we have more lift over here, we also have more drag over here. So it's going to push on this wing and cause our nose to kind of yaw in that direction, yaw opposite the direction of our turn. And again, that's why in a turn, you want to keep an eye on your turn coordinator, make sure it's coordinated. And we'll go more over coordinated turns and stuff for a little bit later. But this is why you have to coordinate turns. One of the reasons is adverse yaw. All right. Any questions before we move on to density altitude? No? Okay. All right. So we've talked about density altitude a couple times, but and the reason I did that in the course and I've done that here is because it is one, maybe top 5, maybe makes the top 5 of the concepts that are harder to understand for students, and it affects different areas, right? It has its feet and hands in different areas. It's in the weather section, it's in performance section, it's in aerodynamic section. So I kind of touch on it a little bit at a time. That's kind of the goal, to kind of build up, and so it's not all one at a time. Here's all the places it affects and gets your head spinning. So I think this is the last time we're going to talk about it, maybe. But hopefully this puts it all together for you. So just like with pressure and temperature, density has a lapse rate, meaning it decreases with altitude. There's a lot going on here, but if you just look at this white part of the graph, that's the troposphere. Don't worry about anything up here. We're not going to be flying up here. This would be if we go to space. But one thing interesting is the temperature. So these 2 lines are the temperature, or I guess the speed of sound. So temperature is red. But if you see, we got that temperature lapse rate. But then once we get to the stratosphere, it actually reverses. And then it reverses back, and it reverses back. We don't have to know about that, but it's just something interesting. If you go onto IFR and commercial flying, where you might get up here, they do talk about that But anyways, so pressure here, we know pressure decreases with altitude here in the troposphere, and also density decreases with altitude. Okay, so as we go up with this y-axis, right, all these are going to the left. They all are decreasing in the troposphere with altitude. So we call that lapse rate. The definition of density altitude is pressure altitude corrected for non-standard temperature. Another way to describe it is the altitude in the standard atmosphere corresponding to a particular value of air density. And then another way, if that doesn't work for you, to describe it is that density altitude is simply just a measurement of density in the air that is converted to altitude. I think it would have been way easier for student pilots if instead of calling it an altitude, we literally just measured the density and just talked about the density, because that's all it is. We were just like we did pressure. We're like, oh, hey, the pressure is high today, or the pressure is low today, or the temperature's high today, temperature low today. How does that affect us? If we just said, oh, the density is low today, how does that affect us? But instead, we've converted it into this altitude, which confuses everybody. But really, the whole purpose is just to give us an idea of what the density of the air is, and I'm going to explain why we care about that. So we know from our lift equation that the density of air directly affects lift. Remember this handy dandy equation? This Greek letter rho was density. It's on the top of this equation. So and this is lift over here. So as this goes up, if this goes up, our lift goes up. If this goes down, our lift goes down. So we talked about how density being good for lift if it goes up. Well, the opposite is true. If the density goes down, our lift goes down. Density has a direct effect on not only the performance of the wings, but also the performance of our engine and our propeller. And it has a negative effect on all three of those when it goes down. So when density goes down, we get less lift, we get less thrust, and we get less combustive output from our engine. So this can cause landing distances, takeoff distances, fuel consumption, and lifting ability to all be affected by a change in density, altitude, or in other words, the density of the air. So just a brief of what, kind of going back to the basics. I know we kind of already covered this, but density is mass per unit volume. So if these blue blocks, these blue little jars are our volume, and these molecules represent, say 1 pound of mass or something. When you have 9 of them here in this volume, you have less mass per volume. When you have, 25 of them, you have way more mass per volume. Tim, yes, less dense air equals less oxygen molecules for combustion. Yep. So a good analogy that I like to use when teaching students is flying through less dense air is like swimming through more or less dense water. Swimming through higher density water, like salt water in the Mediterranean, is easier than swimming in fresh water because you float more in the higher density salt water. Same is true for aircraft and the air. Aircraft perform better in higher density air. Think of it as swimming in the Mediterranean or something salty, really salty. You're going to float a little bit more because the density is higher. All right, density going down reduces the performance of our aircraft in several ways, which I mentioned. We know density goes down with altitude, but it also goes down with increased temperature, increased humidity, and decreased pressure. So we want to know what makes our density go down. Okay, obviously, the higher we get in altitude, our density is going to go down. That's fine. But if we are flying low, like most general aviation pilots do, we're not flying too high off the ground compared to, other large aircraft. What are other things that can reduce our air density when we don't expect it, kind of, right? Well, it's increased temperature, increased humidity, and decreased pressure. So on hot, humid, low pressure days, it can be our performance of our aircraft, again, lift, thrust, combustion, all are degraded in several different ways, from temperature, from humidity, from pressure. And it can be extremely difficult to take off, climb, cruise at speed, reach certain altitudes, stop on landing, etc. The first time I really experienced this was I was doing one of my cross-country flights during the summer, and we fly from, like San Diego area to the east in the summer, and so it'd get really hot. And so it was really warm days, and I think the first one I planned because what Kay was talking about earlier, I wanted to be extra safe and fly at a high enough altitude where I could glide back to an airport. So I picked like 7,000 feet or something like that. 7,500 feet as my cruise altitude. But with my little Cherokee Warrior, I could barely get up to 7,500 feet because my aircraft ceiling was lowered because it was hot and maybe it was a little humid. And so the density of the air was severely decreased, making my performance way less. And it took me forever to climb to that altitude. And that's when I really learned the effects of density altitude. Great. That's every day in Georgia. Yeah. Yeah, I could have oxygen issues potentially as well. Yeah. So let's talk about each of those. So let's talk about each of those and why. Yeah. So Cole, we're going to explain why it goes down with humidity. So with temperature, we have an increase in temperature. So from cold air to hot air, that decreases density. So temperature is a measure of kinetic. It's simply that's all temperature is the measure of kinetic energy of molecules of something. So we're talking about air. So the kinetic energy of air molecules is simply how much they move and bounce off each other. That's their kinetic energy, how crazy they are and how much they're moving around. Molecules are less tightly packed when they have more energy. So as you increase the temperature, they bounce harder off of each other and spread out more. Okay. This is why we talked about that expansion in hot air of our column of air as well. They're impacting each other at greater force and then bouncing further away from each other. It's almost like they have more energy within them and they're pushing everyone else away. They're like, get out of here. I'm mad. And so the whole crowd around them spreads out. That's like hot air. In cold air, they all have less energy and they all start huddling up together. And they get that contraction. All right, so that's temperature. So basically, with increase in temperature, the reason the density goes down is because the molecules spread each other out. They spread out. All right, now humidity. So an increased humidity causes a decrease in density. So increase in temperature, decrease density. Increase in humidity, decrease density. So decrease is bad for performance. So just remember that. So air is mostly filled with nitrogen, N2, and oxygen molecules. So this over here, no humidity. We have mass of air 1. We got oxygen over here, O2, and we got N2. So we got these little molecules, right, floating around in this mass of air with no humidity. Humidity is just a measure of the amount of water vapor in a volume of air. When air is humid, the water vapor replaces the space taken up by nitrogen and oxygen, but water vapor has less mass. So water vapor, H2O, right? Kind of looks like these molecules look like this. It kind of replaces some of these other molecules in a given volume of air. And our water vapor has less mass than our nitrogen and our oxygen. So our mass over here in humid air is less than our mass over here in non-humid air. And remember, density is mass over volume. So if we're decreasing our mass in humidity, we're decreasing our density because density is mass divided by volume. So if we decrease the mass, we decrease the density. And when you're humid, you're replacing water vapor for, nitrogen and oxygen, which are heavier molecules. Water vapor also doesn't have combustion properties. We don't like to light that on fire. We like to light oxygen on fire. So yeah, that's also why our combustion goes down. Does that make sense, Cole? Enough? Okay. Um, yeah, if you think of a good question, let me know. But essentially, just imagine you're taking a scoop of no human air and then you weighed everything in there, all these molecules in there. It's going to weigh like 10 pounds. And then you took a scoop, same size volume scoop of humid air. It's going to have less nitrogen and oxygen that's been replaced by water vapor. And so when you weigh all the molecules, it's going to weigh less because water vapor weighs less. And so you're going to have less mass, and the less mass means less density. Less mass per volume means less density. All right. Last one is pressure. A decrease in pressure causes a decrease in density. So this is different than the first two, right? We talked about increase in temperature decreases density, bad for aircraft. Increase in humidity decreases density, bad for aircraft. Decrease in pressure decreases density, bad for aircraft. So the other two were increases equal decrease in density. This one is a decrease equals a decrease in density. So pressure is a measure of the forces exerted on the outside of a container. So if we imagine this is a force of pressure at 29.92 inches of Hg, and then we have a higher pressure here. Molecules are more tightly packed when under higher pressure and less packed under lower pressure. So here, imagine we have this column of air. We have and we set like a heavy block on the column. It's going to push all the molecules closer together, increasing their density. But if we have a less heavy block that we put on top of this column, it's not going to squish them down as much. So if you think of like if this was like a spring, the heavy block would compress the spring more than the lighter block would, and so you have more density here with the higher pressure and less density here with the lower pressure. So to kind of summarize all this, just a little graphic, high density altitude. Okay, so here's the part of the confusion, the way people talk, the way aviation talk about density altitude. Because when you think of high density altitude, you think of, oh, our density's high, right? No. High density altitude means the density of air is lowered. This is why I don't know why we started talking about density like this. Like, why don't we just say density is low? Why do we say we have a high density altitude? That just makes things confusing. What they're trying to say is the density is making it feel like we're at a high altitude. Okay. So it's almost like, okay, we have lower density. Hey, that's almost as if we're flying at 10,000 feet. And that's essentially density altitude. High density altitude, low density can be caused by high altitude, high temperature, low pressure, and high humidity. Low density altitude, again, when you think of low density altitude, you might think of, oh, low density, because you see the word low density, but it actually means high density. So it means the density of air is high, it's raised. What they're trying to say is the density is making it feel like you're flying at a low altitude where the density is usually higher. Low density altitude or high density can be caused by low altitude, low temperature, high pressure, and low humidity. Any questions there before we kind of we're going to do some scenarios to kind of show you the impact of density altitude that can have on performance. Kind of bring this all home. And we're also going to practice with that density altitude chart. Yeah, so low density altitude equals high density. High density altitude means low density. All right, so I want everybody to get out their figure 7, pull it up on your screen or get it out in your book. It's figure 7 from the Airman Knowledge Testing Supplement. And I'm going to go use the restroom real quick. And then we're going to do some scenario kind of calculations to kind of hammer this home. So give me, if you guys want to take a break as well and get this out, we'll give it about 4 or 5 minutes. Is it figure 8? Sorry, the one that looks like this. Nick says right now the temperature in Georgia for me is 66 F and the humidity is 86. Low temp but high humidity. So low temp for Georgia, yeah, but when we say low temp or high humidity, we're comparing it to the standard atmosphere.
Okay.
So like standard atmosphere, Georgia's usually hotter than standard atmosphere. So although yeah, that's cooler than normal for Georgia, it's about it's close to standard. I think standard temperature is like 56 degrees Fahrenheit. So it's still hotter than standard. I just wanted to point that out. It's all kind of relative to the standard atmosphere. But yeah, but for you who always flies in Georgia, you would feel that. So the lower temperature would kind of increase your density from most days you're used to flying in Georgia. And the high humidity, I don't know what the average humidity in Georgia is, but that for San Diego, that's really high. Wow, we got a lot of people in Georgia. I went to grad school in Georgia. I was there for like 2 years. Georgia Tech. So I was just stayed in Atlanta, but all right, we'll give it one more minute. Make sure everyone's. I know they are undefeated. The Ramblin' Wreck, Yellow Jackets. Talking about college football for those of you that are wondering what the hell we're talking about. All right. So I think that's enough time. So, all right. So have this chart handy. We're going to have you kind of do some practice with it. We're going to talk about 3 different scenarios. And the whole point of this is to show you, all right, so scenario 1, we're taking off from an elevation of 1,500 feet. Our pressure is 30 inches of mercury and our temperature is 45 degrees Fahrenheit. Okay, so a little bit less than that standard temperature. Or maybe at 1,500 feet, it's pretty standard. But anyway, so that's scenario 1. And then scenario 2, the only thing that changes is our elevation. We go up 3,000 feet in elevation. So I kind of want to show you guys what going up in elevation would do to our density, altitude, and our performance. And then the last one, we have increase in elevation from the first one and an increase of 40 degrees in temperature. So I want to kind of compare these 3 scenarios in terms of density, altitude, and performance. Okay. So let's see. Okay, yeah, I don't want to do that yet. All right, so the first scenario, I want us to, using this chart, find our pressure altitude. Okay. Because this chart right here, we need a pressure altitude and we need a temperature. We have the temperature of 45 degrees F, but we don't have a pressure altitude. We just have an MSL elevation. We need a pressure altitude. So we got to use this elevation plus this pressure and this green table to figure out our pressure altitude. So I'm going to give you guys some time to figure out the pressure altitude for scenario 1. Ivan is on it. Quick with it. Tim concurs. Manish concurs. I'll kind of wait till like 5 of you guys have, assuming you guys are all participating, 5 or 6 of you guys before I kind of reveal. I want to make sure. Everyone gets enough time to do this.
Nick, would you mind? I'm really sorry. Would you mind kind of just quickly explaining it again? I was trying to figure out a pencil to kind of do this properly.
No worries. So, we want to figure out our density altitude for each scenario. So, scenario 1, we're given elevation and MSL, pressure and temperature. So our final result is to use this graph, right? But to use this graph, we need a pressure altitude and a temperature. We have temperature, we don't have pressure altitude. We just have elevation and pressure. But we can use this. So the first thing I'm asking you guys is use this green table to find our pressure altitude using pressure and our elevation. Cool. Yeah, I'll show the answer, which I think will. K got 1,000. Ivan, did you change your answer? Oh, step 2. Don't be jumping ahead. I'm going to count that as your step 1 answer. You're wrong. I'm just kidding. All right. So, all right. Mostly 1427, 1546. Okay, so we got some. All right. So, to use this chart, there's 2 different charts. There's a density altitude. So this gives us density altitude. This over here gives us pressure altitude. The reason why they kind of put it right next to it is because we need pressure altitude to use this chart. So usually you're going to be given like an elevation, right? Or an altitude, like a true altitude that is not in pressure altitude. So you have to first convert it to a pressure altitude. So we were given an elevation of 1500 and a pressure of 30.00. So first thing we got to do is we got to look for our altimeter setting, which is our pressure in this first column. So we find 30.00, and then we read off the second column, pressure altitude correction factor. So right here, 30.00 is minus 73. And then we add this minus 73, whatever this pressure altitude correction factor is, because sometimes it's positive. So we add minus 73 to our elevation to get our pressure altitude. So here we are. We got elevation 1500, pressure of 30. That gives us an altimeter correction of minus 73. We add that to our pressure altitude. So adding a negative number is the same thing as subtracting it. So you get 1500 minus 73 is 1427.
How did we get to 1500?
1500 is what we're given in the problem.
Oh, right. Okay.
Yeah.
Okay. I thought we were. finding 1500 on the
No.
chart. My bad.
Nope.
Thank you.
Yeah, all we've done is use this little chart over here. With our pressure, that gave us the minus 73 altimeter correction. We then took our elevation and corrected it using that correction to get our pressure altitude. All right, so now that we have our pressure altitude and we have our temperature of 45 degrees, use this chart to now find, which Ivan did, or he was ahead, step 2, to find your density altitude. So I'll give you guys a moment to do that. Scenario. Oh, see, K was jumping ahead again. Like Ivan. No, that's okay. So we got 800, 900, 1,000. I think Ivan had 900. Darren has 500. Density altitude equals 800. Okay. I have Sam. I'm viewing Sam hard at work because I think he's the last person that
Oh no, I'm
talked.
lost, brother. I'm lost.
Okay, okay.
I mean, I was hard at work, but I'm lost. And I was just about to type in saying, "Is anyone else lost?"
Okay. Well, let's see if we can fix that. All right. So we have temperature of 45 degrees, and now we have a pressure altitude. So now we have temperature and pressure altitude, so we can use this chart here. First thing we do is we find, or sorry, 45 degrees. Did I say 54? 45 degrees. So we find, is that correct? Did I switch that up? No, 45 degrees. All right.
No, you were right.
I think I just have dyslexia. All right. So down here, we find 45 degrees and we draw a line. You can draw it all the way up if you want, if that's easier for you. But basically, we're going to draw it up until we meet our pressure altitude line. Now, our pressure altitude lines are these diagonal lines. And you can see they're 8,000 here, 7,000 feet of pressure altitude here, 6,000, 5,000. So ours is 1,427. Okay, so about 1,400. So about halfway between 1,000 and 2,000, maybe a little bit below halfway. You kind of just got to eyeball it, right? If you wanted to, you could get like a ruler and really measure what is halfway and all that. But you can eyeball halfway. It's pretty easy. You can go a little bit below that. Draw a line from that intersection point, and you can draw a horizontal line as well if you want to do that. And so right at that intersection point of 45 degrees and our pressure altitude of 1427, which is about, again, right here between 1,000 and 2,000 lines, we draw a line all the way over, and this is going to be our density altitude. And these are in thousands of feet. So 1 means 1,000, 2 means 2,000. So we're just below 1,000. I think I just called it 1,000, but if you guys got 900, 850, that is close enough. Yeah. So Darren was using 40 degrees. That's a good learning moment for everybody, because once you get the procedure done on these charts, it becomes human error as to why you get it wrong, right? So just little things like that when I'm talking about like taking the written exam. So just be careful. I know it's kind of hard to avoid when you just do those little mental slips, but happens to all of us. Sam, are you still lost?
No, I'm less lost, but when Tim typed in 4427, then it really sent me off. But no, from what you explained, I understood. I
So
guess I will say one of my weakest points is like anything with like charts and things of that nature. I can do better at other things, but this stuff just, yeah, I'm just slow.
yeah, that's okay. You're not alone. Tim might be jumping ahead as well. I'm gonna have to put him in detention as well. All right, so I did density altitude of 1,000 feet. I mean, again, if you said 900, 850 on the exam, there's gonna be one close enough to that. You can be like, okay, I knew it was a little bit of below 1,000. There's gonna be an answer option on the multiple choice question that's a little bit under 1,000. All right, so let's do scenario 2. All right. Now, I want you guys in the chat. So in the same little message, I want you guys to put your pressure altitude that you get and the density altitude that you get. So do both steps in one. And if anybody needs a reminder of the steps, let me know. Scenario 2, we have the only thing changed is the elevation. So the elevation is now 4,500 MSL. Okay, we're getting stuff around 4,400-ish for most folks. It's too bad we just can't take the written exam as like a group, and we can just take the middle number of everything. All right. So I think we got enough time there. So before we continue to scenario 2, I went ahead and using, I believe, a Cessna 172 performance chart, which again, don't worry that you don't know how to do this. We'll explain how to do this. I calculated the takeoff ground roll distance for the scenario 1. Okay. And so if we're in all these scenarios, I want to think of, okay, we're taking off on a short runway that's only 2,000 feet long. Maybe it's a little private airstrip. Okay. So in scenario 1, where we had, right, 45 degrees Fahrenheit, pressure of 30, 1,500 feet elevation, density altitude about 1,000, that gives us, it's going to take us 950 feet to be able to reach a speed where we can take off. Okay. So about half our short little runway here. That's scenario 1. All right, so now let's talk about scenario 2. So our elevation is the only thing that changed, 4,500 feet. Pressure is still 30, so that means our pressure altitude correction factor is still the same, minus 73. But we just apply this to the new elevation, right? So 4,500 minus 73 is 4,427. I think most of you guys got that. Yeah, looks like most of you guys got that. All right, so now we have pressure altitude and we have temperature. Our temperature is still the same, it's 45, but now we're just drawing our line up higher until we reach our pressure altitude of 4,427. So again, about between 4,000 and 5,000, just a little bit below halfway between those two. And then from there, we draw a line over, and that looks to me like 4,400, 4,500, anything around 4,300 to 4,500, I think would be maybe even 4,200 or 4,600 will get you the right answer on the exam. So I think you guys all got that. I see, David, you got 5,000. Did you do any particular air or? David, can you see why you got 5,000 and not 4,500? Maybe David's gone.
No, I'm here.
Oh, okay.
I could have swore I did this right. So the
And I'm not,
from 45, the lineup from 45 crosses the 4,000 foot pressure altitude at about 4,500. And at the 5,000 pressure altitude, it crosses at about 5,500, and right in between the two of those is about 4,400, which crosses at 5,000.
so what you're doing is you're saying, okay, this 45-degree temperature line, it crosses the 4,000 line at this value. And then you're doing the 5,000, and then you're just finding what's in between there.
Yeah, that's what I was doing.
I mean, that should work, but I think your 4,000 line is down here at, I mean, that would be a dense, if it was 4,000 feet pressure altitude, that would be a density altitude of about 3,900. It looks 3,800. And I'm not trying to call you out or anything. I just want to, there's these little kind of errors that we all do, and I just want to kind of find them for everybody. You know what I mean? So we can fix them.
Use the wrong temperature. I'm on the other side of 50.
Okay.
That's it.
Okay. I'm glad we found it. All right. So I put 4,500-ish again. And so let's see. Right now, I want to just have you guys look at these two density altitudes. Obviously, we're at a different altitude, so they're going to be different. But here, our elevation is 1,500 feet, and our density altitude is actually lower than our elevation. Okay. Remember, a lower density altitude means that's good. It means more density. So it's good for our performance, right? But I think it would be worth it to call out why it's lower. Well, one, our temperature isn't very high, right? Our temperature is lower than standard, a little bit lower than standard. And then our pressure is higher than standard. Standard's 29.92. And then a higher pressure, it increases the density. Remember, it has the opposite effect of temperature and humidity. So we have two kind of factors here increasing our density, which decreases our density altitude. Okay, in this one, we have a density altitude of 4,500. That perfectly matches our elevation. So we don't really have any resultant effects of density altitude going on. Up at 4,500, our temperature is probably a little bit warm for 4,500, right? If using the lapse rate, it might be a little almost standard, but it might be a little bit warm, but then so it's going to lower the density and increase our density altitude. But again, the pressure is high, so that's going to have the opposite effect. So these two kind of cancel each other out. And that's why we have basically no resultant effect of density altitude. All right. And then if we look at, again, so we go ahead and for this scenario too, we calculate our performance. Now with our 2,000, our little short runway, now it takes us 1,450 feet. So why is this? Well, it's because we're just at a higher elevation. And remember, higher elevation means less density in the air. So while we compared it to the previous one, right, we're at a lower elevation, and so we had a lot better performance. So this scenario 1 to scenario 2 is meant to show you the effects of taking off or landing or climbing, whatever, when you're at a high elevation airport. You can see it really increases, almost doubles how long you need to take off just by adding what, 4,000 feet of elevation. So for those flying in, Denver, Arizona, places with higher elevation in the country, this is something to think about. All right, so let's go to scenario 3. Scenario 3, again, has 4,500 feet, 30 pressure. That's the same, but now our temperature is up to 85 degrees. So I'm going to let you guys calculate both the pressure altitude and the density altitude for scenario 3. So I'll give you guys a moment to do that. Some of you guys are on it already. Nice. Looks like we got density altitudes of around 7. We got 7,400, 7,000, 6,900, 6,900, 6,900, 7,000, 7,000. So yeah, hint, our pressure altitude did not change from scenario 2 because our elevation and our pressure did not change. So we should still have 4427 for our pressure altitude. Okay, so mostly around 7,000. All right, so just to show you again, we still have 4,500, we still have 30, so we're still using this correction factor of minus 73. When we apply that to 4,500, we get 4427 for our pressure altitude. So we're still going to be going up to somewhere in between 4,000 and 5,000, but where we go depends on our temperature. So our temperature has gone up by 40 degrees. So we're all the way over here now, and up at this high elevation, that's going to have kind of a double whammy effect on our density altitude, right? Higher elevation decreases our density, high temperature decreases our density. So if we go over here to 85, we draw a line all the way up to where our in between our 4,000 and 5,000 pressure altitude lines, again, right, close to the middle for 4427. And we draw a line all the way over. We're going to get about 7,000 or just below 7,000. Just below 7, which means 7,000 for our density altitude. So those of you that got 6,900 or 7,000, which I think it was most of them, most of you guys. Manish got 74. That's within, I think, the realm of maybe just a little eyeballing things a little bit off. It's getting a little bit outside the range of kind of eyeball error, I like to call. So you want to be careful and just make sure you're using like a ruler and stuff. But yeah, good job. So, all right. So now look at so from scenario 2 to scenario 3, the only thing we changed was the temperature, and look how much bigger that density altitude is. It increased by 2,500 feet. That means our density decreased a ton just by an increase. I mean, it's 40 degrees. That's a large temperature increase. But what does that have on the effect of our taking off? So here, if we were to compute our Cessna 172 takeoff ground roll distance, we get 1760. So now we are dangerously close to the end of our short little runway. So if we're up at an altitude, an elevation of 4,500 feet, and it's hot out, we're taking off a short strip, probably not a good idea, right? 1760, yes, that is less than our runway, so you technically could do it. But what if your calculations were wrong, right? Kind of want to have about 20% margin on this number here to be safe. Also, what if what if you taxied onto the runway right here and didn't taxi at the very end? So you have less space to get up to speed. What if what if the runway surface was a little bumpy, slowing you down? What if your aircraft engine wasn't performing at 100% and it took you just a little bit longer? You need to have a good buffer, and 240 feet is not it. It should be in the range of thousands, because also, what if you get right here and your takeoff speed is 60 knots and you're at 57 knots and you're just like, and so you decide, you know what, I'm not going to make it. I'm going to come to a complete stop. Well, now you don't even have enough room to come to a complete stop. So really your go, no go point should be like right here, which would have only been in the first scenario. So these are all kind of considerations you got to think about with elevation, pressure, temperature, and humidity, especially if you're taking off from short runways, landing on short runways, having to climb over obstacles, all because of density altitude. All right. That's the show.
I have a question.
Yep.
So how can we calculate the takeoff ground roll distance?
So you use performance charts in your pilot operating handbook for your aircraft. We'll get to that in a future lesson, so don't worry about that right now.
All right, thank you.
But you guys did pretty good. By the third scenario, I think you guys basically all got it. Everyone that put it in the chat, at least. All right, so pull up the homework. So let's talk about the homework, and then we're going to do the FAA written stuff. Okay. Almost forgot about that. So we're 29th. Yes. So we covered this stuff. We're going to cover how to schedule the FAA written. And we got supplemental oxygen, hypoxia, hyperventilation, ear and sinus concerns, motion sickness, spatial disorientation, and illusions as added homework. So you got to do these quizzes and then also read through or listen through these lessons and do those quizzes by Saturday, because we're going to meet. Remember, we're meeting on Saturday instead of Friday. We're meeting Saturday morning, 8 a.m. Pacific, due to Halloween complications. All right. If there's no questions on the topics, I'm going to go on to scheduling the written exam. Okay. So let's look at when we're thinking we're going to be done here. So right now we got November 19th. We'll be all done with the homework and we'll start to do our test prep and endorsement. Okay. So to do that, there's 3 practice tests. Each of them depends on you, but you'll get 2 hours to take each of them. Each of them should take about an hour though, on average for the average student. But if it takes you longer, don't freak out. Don't think you're not an average student. It doesn't mean, I mean average in like how long it takes you to take tests. That doesn't mean you're less than average. I just want to say that. I for one, I take my time on tests and I would take the whole 2 hours. So I would be less than average in terms of test taking time. Anyways, so this, I expect this should take about a couple days for you to take those 3 tests. And then if you need it, we'll give you more tests and have you review. So I think a week from the 19th, like the 26th, I know we're getting into like Thanksgiving time. So that's when is Thanksgiving? Stuff like that.
27th.
27th. Okay.
Yeah.
So yeah, maybe the 24th, 25th, 26th would be good days. Or if you want to kind of wait after the Thanksgiving break, maybe kind of I'm going to let you guys choose, but I do want to encourage you guys to set a date today. Okay. So if you want to kind of have that extra break from work or whatever to take your test, that might be a good idea. And maybe we schedule it December 1st. Okay. So I'll let you guys decide on the date, but I do want to recommend you guys doing that. All right. So the first thing we got to do, and let me send this here in the chat. You all have to make an account on IACRA if you haven't done it already. So here's the IACRA website. So you would just register right here. And you don't have to do anything yet. You can literally just make an account. And what that's going to do is it's going to give you a number, a federal tracking number, FTN number, or maybe it's FAA tracking number, but it's FTN. And we need that FTN to schedule the test. Okay. So even if you haven't started flight training or anything like that, you can still do this. You just literally make an account with your name and email, maybe your address. I can't remember. If you already have, you just need to log in. And so I'm going to log in here. Don't want you guys to see my password. I got to look it up, but I'm going to go. And if you guys want to follow along and do this with, I'm going to log in here so I can pull it up so you guys can see what I see. All right. I am logged in. So it's going to look at this. You accept the terms of service. And then if you want to do your student pilot application, if you haven't done that yet, you would do start application and you would choose like student pilot airplane. And that starts your application for a student pilot. And then you would have to finalize that with your flight instructor. So once you have a flight instructor, they will just kind of sign you off. They have to make sure you can read, write, speak English. You are who you say you are. You have an identification, that sort of thing. So they just have to finalize that in the system. You don't have to have a student pilot certificate until you fly solo. So it's a perfect thing to just do with your flight instructor on your first lesson. But you can start that application if you want. But you don't even have to do that to take the written exam. All we're looking for is this number here. Okay. So this FTN number. All right. End of January, Jackie, I would say is too far. Yeah, you want to make sure it's all fresh. Just get it done before Thanksgiving. Get it out of the way. Right? Then you'll be done before Black Friday and all that rush. Come on, Jackie. You can do it. All right, so we got that FTN number, right? It's so scary. You got this. You got this. But also, as I'm going to show you, you have 72 hours to reschedule, but I recommend scheduling it for before Thanksgiving. And then once we get to the point where you're taking the practice test, if you're like, I'm not ready, you can reschedule. All right. Okay. So we got our FTN. Now here is, if you type in FAA PSI on Google, you cannot find, I don't know how to find this website. So I'm going to give you guys this website. You go to faa.gov/training testing, blah, blah, blah. I just sent you the link. You scroll down. Honestly, this is the only place I can find this link. Knowledge testing, PSI services, knowledge testing centers. You click on that, and let's hope this is working. All right. And it takes you to this PSI website. That's, if you go to the regular PSI website, it looks totally different. This is like a special FAA version of the TSA website. And then you're going to have to create an account here as well. All right. I'm going to sign in. If you guys want to create an account now, while I do that, I think that would be a good idea.
Can you come back where you press that link?
Like,
Okay,
this
got it.
thing,
Thank you.
yeah, this link right here. Yeah. Here, let me send this link as well. By the way, one thing that confused me is once you make your account, I think your username is just your email without the at after it, and they want your username on login, not your email. I think I was having troubles earlier. It could have been just because their website is down.
Mine says that the information does not meet the eligibility requirements. Please ensure all your information is correct, and to the best of my knowledge, it is 100% correct.
For IACRA,
For True Talent PSI, I've already done IACRA, logged back in. It was a long time ago. And then I've came into here, I've put my FTN in there, put my first name, last name, I've hit continue, and then it says information does not meet the eligibility requirements. Please ensure all your information is correct.
so you put your name,
Yep.
your what all information did you input?
It's just your FTN, your first name, and your last name. And I
Did you
tried both my
did you copy
go
and
ahead.
paste your FTN?
Um no, because I had it in my notes on my phone, so I was just taking it from there. So I wonder if maybe
Maybe there's like the number before it, or if you copy and paste, sometimes you get a space when you
is it
paste it.
going back to the FAA one where with the IACRA, is it the certificate number or the application?
It's the FTN number. Do you see? Let me zoom in on that.
Well, I'll be damned. I have a totally different FTN than what I had here. Like it's a completely different number. Okay, never mind. Thank you.
Yep. So yeah, so I think you're you're a little ahead of me, Sam, on this, but like right here, you're gonna see there's no way for me to, this is my test account. Like this isn't my actual like IACRA and PSI, but it's my test account so I can teach students what to do. And for some reason, like I started this application and I can't get rid of it. And I started this and now I can't get rid of it. So what I'm going to do with you is I'm going to schedule the IFR in front of you guys. But you guys would do the private pilot and I'll show you how to find that. Yeah. So what you're going to do. So hold on, guys. We're going to do that. Don't jump ahead. So you'd make your profile like Sam did with your FTN. Make sure your FTN's right. Then what you want to do is you want to go to up here to select. Okay. And we're going to select a test. And if you just type in private, that will pop it up. It's called Private Pilot Airplane, or PAR. And it should be recreational and private pilot as a category. So PAR, private. If you just search private, it should show up. And then you would select that. I'm going to do the instrument one because it doesn't like that I already have the. So I'm going to do this one. It'll show you guys the same stuff. It's just you guys will be doing private. Okay, so I say submit. Okay, this says, did they change their policy? If you arrive at the test center to take an exam and it is determined you selected the incorrect exam or you are not authorized to select the exam, you'll be required to pay again for the correct author. There are no refunds otherwise. So let me do this because I wanted to look up. I thought that this used to be that you could reschedule. So let me look that up here. Can I reschedule PSI FAA exam? Test taker support. I want to find this out for you guys. Can I cancel and or rebook my test appointment via the PSI website? Many test appointments can be canceled and or rebooked through logging into your account. Typically, we allow you to book 1 day prior if space is available, and we require 2 business days to rebook your exam without penalty. Okay, so 2 business days. So set an alarm, whatever date you guys choose, set an alarm 3 or 4 days before. Cole, do you not see my screen? Okay, well, I'll get there here in a second. I just wanted to make sure that you can reschedule, and it says 2 business days prior. So set an alarm Yeah, school experience. Yeah, so hold on, guys. I'm getting there. So I'm gonna say yes. All right, so all of this is really confusing, but this first one, it makes you enter the number of exam attempts, and obviously we haven't taken it yet, but if you have it, I guess if you've already taken it once, then you would say two, because it includes the time you're about to take. So we would, since we haven't taken it, it includes the time we're about to take, so we got to put one. And then it says school or other. Okay, so we are in the other section. So the other section is online ground schools, ground school, with a one-on-one with an instructor that you pay, ground school, even at a flight school. These school one is for like if it's like a large part 141 school or like a university. So we would click other. Now down here, you can read this, but it just says what since you selected other, you're going to need an endorsement. Okay. If you selected school, you would need a certificate of completion. We are other, so we just need an endorsement. We will provide you that endorsement after you take the practice exams. So what you're going to do is you're going to say other statement or endorsement of eligibility. Okay. And then we're going to click continue. If you need accommodation or not, if you have like a disability or something, you can look into what accommodations they have. I'm going to just say no. Confirm that. All right, now we just find a testing center near us. This is going to be a lot of good information for the exam. Okay, they say arrive. If you're more than 30 minutes late, you're gonna have to pay again for it. It's not gonna work. They recommend going 15 minutes prior. You're gonna have to show them your ID, so a valid ID, and they have a testing matrix from the FAA of what makes an ID valid, and then you're going to have to have the endorsement from us. It also talks about the allowed materials, okay, and the prohibited materials. So all models of aviation-oriented calculators may be used, including small electronic calculators that perform only arithmetic functions, blah, blah, blah. So basically, you can use E6Bs. You cannot use programmable calculators or anything like that. You can use applicants may use scales, straight edges, protractors, plotters, navigation computers, blank log sheets, holding pattern entry aids, and electronic or mechanical calculators that are directly related to the test. Okay, so you'll bring your plotter tool and your E6B, and then they will provide you the rest, pretty much. You can bring a regular calculator if you want to, but as I mentioned, these testing sensors should have them right on the computer. If you want to call them and ask them, I actually did that on my test. I called the testing center and I said, hey, do you guys supply a calculator? And they said, yeah. Okay, so understand and agree. All right, then you're going to enter your postal code and you can select the distance, maybe start close. And if you can't find one, you're going to have to drive a little bit. And then you want to click a date range. So we talked about, let's say we do December 1st. So say I'm going to look at December 1st, and I think they're open on weekends, some of these too. Say December 1st through the 3rd is when I want to take it. Let's search. All right, and bam, it's got testing centers. Okay, it says 12 miles away from my zip code. And it's got the address here. It's got 28 miles, 28 miles. Looks like this closest one. It's got a lot of appointments. Got some on the 1st, 2nd, the 3rd. Plenty of options here. So I can just, let's say I want to do it in the morning, get it over with, have a good day afterwards. You just click on that and then click schedule. And then click on schedule, and then you're going to have to pay. Had to change, Tim, you said had to change pass. What do you mean? Sorry, I'm not sure what that means. And then here you just enter your payment information and complete the payment.
It's asking for an authorization category at the end
Authorization.
under school or experience. I'm just trying to catch up.
Oh, yeah. So you would check other, because we're not like a university. So you
So
did,
other statement or endorsement.
yeah. So you click other on the little radio buttons, and then after that, you
Right.
would click other statement or endorsement. Yeah.
Gotcha.
Did anybody else not even able? I have not been able to follow any of this, Nick. When I went on this PSI True Talent, when I finally got my correct FTN number, I had this setup multi-factor authentication application, which is a mouthful. I've attempted to do that with no such luck.
Oh,
Like I
okay.
literally have been trying to do that for the last like 8 minutes.
Okay, sorry. Yeah,
No, that's fine.
I already had mine set up. So yeah, they require
Okay.
multi-factor authentication. So remind me what the options they give for you for that.
So the first thing I've got to do is download the app. I did that. I've then scanned it. I've then given the verification code, and it just doesn't work. I mean,
Yeah. So yeah, you download Google Authenticator is the app, and then
yeah,
and then through Google Authenticator, there should be a plus at the bottom.
Yep.
And you press that, and then it'll bring up like a camera. Or you say scan QR code, and then you scan the QR code, and that doesn't work.
Correct. When I do that, I hit verify.
And you enter in
now it's made me look like a fucking idiot. Sorry, like an idiot. Because now it worked, but it definitely didn't. It definitely did not work.
Of course. No, you're good. So Cat on IACRA, yeah, it would be student pilot application. But you don't have to do that yet if you don't want to. You just need the FTN number from IACRA. As soon as you make an account on IACRA, your FTN number is going to be on the top left when you log in. I can show you that right here. Right here, FTN number. If you want to start your student application, you can. You don't need your student pilot certificate until you fly solo. So usually your flight instructor will just do that with you. Because the first several lessons are going to be, you're not going to be flying solo. So you have time to do that with your flight instructor. So all we need right now is this FTN. So that we just got to create an account. And then once we have the FTN, then we can create an account on PSI. Ivan's got it scheduled. Nice. So Sam, let me know if you get stuck at all. I can kind of show you again. You go to select.
Yeah, I'm going to need you to here in a minute. Just give me 1 second.
Okay.
Thank you.
December 6th. Nice, Cole.
It's a like private pilot airplane, right?
Yeah, so if you search private pilot or private, it's private pilot airplane PR. Yep. You do not use the same website for a check ride. Check ride is like old school. You just have to find an examiner and contact them. It's like the Wild West, man. There are some websites that show examiners in the area.
Okay, sorry. I think I'm up to where I need to be. I'm now searching in. I type in private pilot, and it's the private pilot airplane in brackets PAR.
Yep.
Okay.
So you'll select that. Now, unfortunately, I'd have to do another one to show you, but I think the next thing you're going to see is something like this. Pre-exam data collection.
Yes, I'm on that right now.
Hold on, November 21st. I think that might be a little too close, Darren. I'd feel comfortable as the earliest, like November 24th for you guys. But that means like right here on the 19th, you're really going to have to you're going to have to show us with 3 consecutive practice tests that you're getting 80 or above. So it depends on how confident you feel in that. If you think you can do that by the 20th, but we also need a day to kind of review your stuff. And so, yeah, I would say 24th at the earliest. Sam,
Yeah, so I'm here. So I hit the exam attempts one. I go to the school or experience. Is it school or other?
you go to other,
Okay, thank you.
and then you want to do other statement or endorsement of eligibility. So that's
Other
just say,
statement or endorsement of eligibility. Alrighty, thank you.
yep, that just says that we're gonna give you an endorsement. That's your ticket to take the test.
Okay.
The cost is $175. This is on YouTube, Cole. It's also in our course. You go to I think it's here. Or no. It's in the step 2 course, which I can't do on my test account, of course. But so once you finish step 2, the first lesson has that video, but it's also on YouTube. Let me get that video for you guys.
Hey Nick, this is Sherry. While you're getting the video, my pilot teacher, I took a few lessons before I decided to do this intensively. And I got a student pilot card. Does that mean I registered on IACRA?
Yes.
Is that what that means? So the certificate number is the number that I use inside PSI then.
No, I don't think you want to use your FTN, and I don't think that's on your certificate. I think you have to
It's
log.
not, I don't see it.
Yeah, you have
So
to.
now I have to figure out my stuff. Okay,
Yeah.
thank you. Sorry for that
No,
dumbness.
no, you're okay. I love to see that. I'm the second video that pops up when you search on YouTube. Love to see that. Good SEO going on there. All right. All right. Anybody else? Sam, how you doing?
Yeah, I got a date. I'm about to go
All right.
pay for this sucker. Mine's not till December 12th, but it just gives me a little bit more time to study, I guess.
Okay. No problem.
But yes, I'm on payment screen now, so I'll be right back.
All right.
Nick, when this class is all done for tonight, could I keep you on here, borrow you for 5 minutes instead of calling you? Is that
Sure. Yeah.
would that be okay?
Yeah.
Thank you.
Nice, Tim.
Nick, also another question, and sorry, I think I've asked about 4,000 questions today. How much truth is there, if any, on so my personal goal, I don't know about anybody else's, is to do this for a living. So one day, big airline or big company or whatever might want to hire me potentially. Is there any truth into if you say I don't know, not putting this into, the world, it's not going to happen, touch wood, I'm going to pass with flying colors. But if you fail things, say multiple times at certain different stages, do they look at that? I know for check rides, they certainly do, right? They look at, but same for this. I guess my question really is I'm guessing you should really only book anything, not just this, but all of them, if you really feel like you're actually going to pass them. Is that fair to say?
Yeah. So, I mean, if you were, Sam, if you were hiring somebody and there was 10 applicants, would you look at that?
Right. Yeah.
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 So is it gonna,
That's what I've heard.
is it,
So
is it not, is it gonna make you not eligible? No. Is it gonna mean
Right.
you can't get hired? No. Is it gonna improve your chances of getting hired? Yes.
okay.
Yeah.
Cool. Thank you.
Mhm.
I was just curious if that was one of those myths that people say in the aviation
Yeah.
world just to kind of like make you or whatever, but I think there is some truth behind it.
Yeah, definitely. Sure.
So I'm looking at some dates here. We said we're doing reviews like the 19th, the 21st.
Yeah, so let me pull that up for you. So yeah, so I want you guys to have the 3 practice tests done by the 21st, but that doesn't mean you'll be ready, because if you don't score well enough on the practice test, we'll have you review some things, and then maybe a review. I'm thinking we might do a review session on the live, and then you have to take some more practice tests. So I would say that's why I said like the 24th is probably the earliest I would schedule it, to give you that room to get ready and get your endorsement. All right. Well, Kat, you're authenticating. How's that going? Anybody who like is behind or anything too, like even if we drop off that YouTube video I sent, I don't know if it was clear, but that is this process that we just went through. So if you need another reference after this, that YouTube link that I just sent will help you do that. All right. Well, if that is it, just your homework. Yeah, it's a really finicky website, especially right now. I was having issues with it today. Kat, reach out if you have any questions as well, okay? Yeah. All right. So yeah, homework here again, and great work, everybody.